In the first video on this series, we traced the evolution of the framework governing seismic design from the deterministic era where seismic design was based on an earthquake of a given magnitude through to the current risk-based phase that is built on the probabilistic framework. We showed how the introduction of the risk-based framework helped to ensure that structures are designed to have uniform safety against collapse. Our discussion demonstrated that the term risk-targeted is not just a throwaway descriptor. Rather, it marks a conceptual shift in how design ground motions are calibrated. While our discussion of the overarching concepts was thorough, we did not go into the details of how exactly this risk-based framework is wired into the probabilistic framework, which is the bedrock of modern seismic design. It is important to note that engineers designing conventional structures may never directly engage with the analytical foundations of the risk-targeted concept. However, understanding how this framework evolved remains important, especially for those seeking to go beyond minimum compliance. Gaining insight into this framework deepens professional judgment and strengthens the ability to apply code provisions thoughtfully. Let us look at some of the reasons why this is important. First, it helps engineers move beyond procedural code compliance and begin to understand the deeper meaning in the parameters used in seismic design. Rather than treating seismic acceleration parameters as abstract inputs from a table or software tool, engineers begin to appreciate what these numbers actually represent in terms of structural performance, collapse risk, and societal safety objectives. This shift in perspective empowers engineers to engage with code provisions not just as rules to follow, but as expressions of a calibrated balance between hazard, performance expectations, and public policy. The second reason follows from the first. Having this understanding equips engineers with the knowledge to interpret code requirements critically and contextually, especially in complex or irregular projects where design assumptions may need to be challenged or defended. Understanding the relationship between hazard, structural response, and collapse risk allows designers to make more informed decisions, whether they're evaluating a code exception, choosing a seismic force resisting system, or explaining their rationale to a peer reviewer or building official. Building codes such as the IBC have provisions that allow the use of alternative means and methods. Using such methods requires a thorough understanding of the code and the code's intent. Third, it gives engineers a stronger voice in interdisciplinary conversations about risk, resilience, and performance objectives. As building codes evolve and performance-based design becomes more mainstream, engineers who understand how collapse risk is quantified and embedded in the seismic parameters are better prepared to lead those conversations. Finally, and perhaps most importantly, it empowers engineers to communicate clearly and honestly with their clients about what the design is actually accomplishing from a risk perspective. Most clients assume that meeting code requirements means their building is entirely protected from collapse against any future earthquake without realizing that the code sets a minimum threshold which for ordinary non-essential structures is a 1% chance of collapse in 50 years. When engineers understand the principles of risk calibration embedded in the seismic design process, they are better equipped to explain the true meaning of code-level performance to clients. This knowledge enables engineers to communicate that code-compliant design achieves a minimum acceptable level of safety, which may not necessarily be the level that best aligns with a client's operational, ethical, or long-term goals. In doing so, engineers can help clients make informed decisions about whether to design beyond code minimums. Failing to have that conversation is a disservice to a client who might be interested in a more conservative design than code minimums. The process of seismic design typically begins with the engineer obtaining seismic design parameters published by organizations responsible for their development and regulation. Among the most critical of these parameters are the risk-targeted maximum considered earthquake spectral response accelerations, which form the foundation for modern seismic design. As the name implies, these values have already been processed to incorporate the risk-targeted framework, which is an approach that calibrates ground motions to achieve a consistent probability of structural collapse across different locations. In this presentation, Our goal is to trace how this risk-targeted framework is embedded within these values, ultimately allowing them to carry the risk-targeted designation. This is as much a historical discussion as it is a technical one, because understanding how these parameters came to reflect calibrated risk requires looking back at the developments that led to the current approach. We will not look at the historical evolution of the seismic design framework. We already did that in the previous video on the evolution of seismic design in U.S. building codes. However, we will look back at a singular historical project that was instrumental in defining how this calibration is achieved. The original source of the raw seismic acceleration parameters is the United States Geological Survey. This is a science bureau within the Department of Interior responsible for monitoring and mapping natural hazards including earthquakes and ground motion across the United States. These raw seismic acceleration parameters are grounded in what is known as probabilistic seismic hazard analysis, which forms the analytical foundation of modern seismic hazard mapping. Rather than focusing on a single worst-case earthquake scenario, the probabilistic seismic hazard analysis integrates data from multiple possible earthquakes, varying in magnitude, location, and frequency to generate a hazard curve for a specific site. This curve expresses the annual probability that a certain level of ground motion will be exceeded. The United States Geological Survey uses this probabilistic framework to produce national seismic hazard maps. For each site across the country, these maps assign ground motion values such as spectral acceleration at short periods or SS and spectral acceleration at a 1-second period or S1, typically corresponding to a 2% probability of being exceeded in 50 years, which translates to a return period of approximately 2,475 years. These values represent the hazard only. They quantify shaking intensity, but they don't yet tell us how structures will perform when subjected to that shaking. This is a key distinction. The hazard maps are probabilistic in nature, but they are not yet risk-targeted. At this stage, the ground motions reflect the statistical likelihood of shaking but not the consequences. In short, knowing how hard the ground might shake is not the same as knowing how likely a building is to survive. This gap between hazard and risk became increasingly apparent in the end of the last century and early 2000s. The structural engineering community lacked a clear, quantifiable way to link ground motion intensity to collapse probability. Researchers understood that buildings responded differently to the same ground motion, but there was no framework to capture those differences in a way that could inform design ground motions or validate system performance. This gap began to close with the publication of FEMA P-695 in 2009 by the Federal Emergency Management Agency. Although the study's original purpose was to evaluate whether seismic force-resisting systems being considered for code inclusion could meet acceptable performance goals, its methodology introduced collapse fragility curves to the hazard-risk conversation. By simulating the behavior of archetype buildings under increasing seismic intensity, FEMA P-695 quantified the probability of collapse as a function of ground motion, system type, and building characteristics. Once these fragility curves were overlaid with hazard curves from the probabilistic seismic hazard analysis, a deeper issue came into focus. Buildings designed using the same probabilistic seismic hazard analysis-based ground motions could have wildly different collapse probabilities, depending on the steepness of the local hazard curve and the fragility of the system. In some cases, structures that met code were estimated to have more than a 10% chance of collapse in 50 years, which is far beyond what most stakeholders would find acceptable. In others, the design was overly conservative. The implications were profound. Even though FEMA P-695 was not created to solve the hazard-risk inconsistency, it demonstrated that hazard alone was insufficient, and that risk-informed design ground motions were needed to ensure more uniform safety across regions and systems. This realization led directly to the development of risk-targeted ground motions, which adjusted the mapped hazard values to achieve a consistent collapse probability which is typically set at 1% in 50 years for ordinary buildings. It was a foundational shift in how we define, map, and use seismic parameters in design. With the need for uniform risk clearly established, the next challenge was to embed this consistency into the seismic design process in a way that could be used by engineers in everyday practice. This is exactly what the ASCE 7 standard accomplishes. Rather than requiring designers to perform complex probabilistic analyses or run collapse simulations, ASCE 7 integrates risk calibration directly into the mapped ground motion values for use in design. The key to this process lies in the concept of risk-targeted maximum considered earthquake ground motions. These are not the raw values from the USGS probabilistic seismic hazard analysis output. Instead, they are adjusted spectral accelerations that have been scaled, based on system fragilities and hazard curve shapes, to ensure a consistent probability of structural collapse. For ordinary structures, the target is a 1% chance of collapse in 50 years. This approach is designed to achieve performance equivalency across different regions and building types, even when the underlying hazards differ significantly. To make this system usable, ASCE 7 relies on collaboration with the USGS to provide risk-targeted ground motion maps. These maps serve as the foundation for tools such as the ASCE 7 Hazard Tool, which is freely accessible online. When a designer enters a project location into this tool, it returns the risk-targeted values that are already adjusted to meet the national risk objective. The engineer is not presented with the raw seismic hazard data. Instead, the tool delivers values that have already been processed to reflect risk-based design intent. What this means, in practice, is that the entire risk-targeted framework has been front-loaded into the seismic values designers use. Engineers do not need to estimate collapse probabilities or adjust for risk regionally because the output provided by tools such as the ASCE 7 Hazard Tool has already been processed to include these elements. As a result, two buildings designed to meet minimum code requirements as far as seismic forces are concerned in different parts of the country can be expected to have roughly the same probability of collapse, even if their exposure to seismic hazards differ dramatically. This seamless integration of advanced probabilistic data, fragility modeling, and code-level simplification represents a major evolution in seismic design. It ensures that life safety performance goals are met more uniformly, more transparently, and more reliably than ever before. We have distinguished between the raw probabilistic seismic hazard parameters and the post-processed, risk-targeted seismic acceleration values used in design. A natural question that arises at this point is whether these raw hazard values hold intrinsic value, or whether they exist solely as intermediate inputs for generating the risk-targeted ground motions defined in ASCE 7. This question is important because it sharpens our understanding of the fundamental distinction between hazard analysis and risk-based design, and it clarifies the broader role that hazard data plays across multiple sectors. The raw probabilistic hazard values are not just a stepping stone to risk-targeted design values. They are a foundational scientific dataset with broad applications in and beyond the structural engineering design codes. Here are 5 applications. First, they are used in performance-based earthquake engineering. Engineers performing custom risk analyses for hospitals, nuclear plants, or tall buildings often start directly with hazard curves. They combine these curves with structural fragility functions to estimate expected damage and downtime as well as economic loss. Secondly, there is insurance and catastrophe modeling. Insurance companies use raw hazard data to build loss models across portfolios. They apply vulnerability functions tailored to specific assets or construction types. These models don't assume a single code-level target. Rather, they assess risk across a range of seismic hazard thresholds. Third, this data is used in the design of critical infrastructure. For utilities, transportation networks, and lifeline systems such as pipelines and bridges, engineers often perform site-specific probabilistic seismic hazard analysis. These analyses may use custom performance goals unrelated to ASCE 7 risk targets. Fourth, This data is used in public policy, land use planning, and emergency preparedness. The Federal Emergency Management Agency, or FEMA, as well as local jurisdictions and planning agencies, use hazard maps to identify high-risk zones and to prioritize retrofit programs and establish emergency response scenarios. These applications are hazard-driven and not necessarily tied to any singular building code. Fifth, the raw probabilistic hazard values are used in scientific research and model validation. Seismologists, geologists, and risk modelers use the raw maps to compare regional hazard trends, to evaluate the sensitivity of hazard to model assumptions, and to test alternative ground motion prediction equations. In conclusion, the raw probabilistic seismic hazard parameters are used across disciplines and industries where structural design codes are either not relevant or not the only concern. The risk-targeted framework is just one specialized use case that builds on these values by combining them with structural fragilities and policy-driven performance goals. If you have enjoyed this video, please don't forget to give it a thumbs up and subscribe to the channel, and do not forget to hit the notification bell so you never miss an update. Your support helps us keep creating great content, and we'd love to have you join the community. Thank you for watching.